sometimes we want to find the domain and range of a function from a graph of the function. So here's a graph right here. We'll call this f of x. And remember that the domain is the x values, and the range is the y values. Okay, so we want to look at this graph, this function, and determine what are all the x values allowable in this function, and then what are the y values that come out as outputs. So let's see. One way to think of this is what parts of the x-axis are covered by the function. So what parts of, this is going to be for the domain, of x-axis are, I'm putting this in quotes, covered by the function. Okay. So this function continues off, right? It keeps going and going and going. It doesn't just stop where the graph stops. So we have to imagine this function continuing off, and it gets wider and wider and wider and goes out to infinity. So let's color in all the x values that are covered by this function. Well, everything in the middle here is clearly covered because the function is above it, right? So this stuff is all covered right in here. Okay, but then this is also covered. And by covered, I mean, I'm imagining squashing this function down onto the x-axis. I guess we could do this like so. Let's imagine squashing this function down onto the x-axis and asking ourselves which, if we did that, which x values would be covered. So this goes off infinitely wide here to the right. So if we just kept squashing down, we would get all of these x values covered. And it would just keep going and going and going. Same thing with over here to the left. If we were to squash this down, this would just keep covering the x-axis, and it would keep going off to infinity. So, what does that tell us? It tells us that for the domain, since this goes out all the way to positive and negative infinity, the domain is negative infinity to infinity, because I'm answering the question of which of these x values are covered by the function. Let's take a look at the range. Similarly, the range is asking what parts of now the y-axis are covered by the function. So what parts of the y-axis are covered, putting that in quotes here, covered by the function. Okay, so now we're imagining, and there's a few ways to think about this, but now we're looking at the y-axis instead of the x-axis. So any part of the y-axis that has a function, I guess, corresponding to it would be covered by it. We can imagine squishing this function down onto the y-axis. Right? If we were to squeeze this whole thing down and just kind of smash this entire thing down just onto the y-axis, this would get squashed here and here, everything would get squashed, and what all would be covered? Well, this would be covered up until 4. This is 4 here. I don't know if you can see that number. This is 4 up here, and it would be going down, 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 like this. Alright, and since this function keeps going down infinitely, this y-axis would get covered down, 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 infinitely by this function. Okay, so the range then, how do we represent this? Something that starts out down here at negative infinity and comes up, 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 and stops at 4, but it does hit 4. Note that the value 4 is actually reached. Okay, so let's see here. So the range then is negative infinity, and then goes up to 4, and it actually hits 4, so I'm putting the closed brackets on 4. Okay, so range gives you the y-axis, and domain, you work with the x-axis. Let's try another one. This function represents a line. All right, so a line that just keeps going, so don't be confused by that. It just keeps going off in off into the infinities there. What's the domain of this? Okay, so the domain, we're collapsing this down onto the x-axis. We're asking what parts of the x-axis would be covered. Right, if we were to just let this function collapse down and cover the x-axis. Well, it just keeps going and going and going. So what parts would be covered? Right, if we just if we squeeze this thing down onto the x-axis, it would just keep going and going and going. So the domain is all real numbers, negative infinity to infinity. Now let's look at the y-axis. The y-axis will give us the range. Okay, so now we are squeezing this function down, and we're asking what parts of the y-axis are covered in any way by this function. So we kind of squeeze it down onto the y-axis. Well, let's see. All of this is covered right here, and it just keeps going and going and going up in that direction. And all of this down here is covered, right? And it just keeps going and going and going down in that direction. So how do we represent that when the whole line is covered? Well, again, it's negative infinity to infinity. There's the range there. So for a line, and this holds true for most any line, as long as it's not a vertical or horizontal line, the domain and range are always going to be infinity. Let's look at another one. Okay, so here's a horizontal line. In fact, this is the line y equals 2, because it goes to the point 2 right here. So we want to find the domain and the range of a horizontal line. Domain and range. Okay, so maybe you can already spot the domain. What's the domain? You tell me. Did you say negative infinity to infinity? Because that's correct, right? Remember, we're collapsing this down for the domain, right? These are the x values. Range is the y's. So for the domain, we're collapsing this thing down or squeezing it down onto the x-axis, and we're saying what parts of this are covered. Now, again, this is a line that keeps going here. So if we were to squeeze it down onto the x-axis, the entire axis would be covered by this function. So the way we write that is negative infinity to infinity. Okay, let's take a look at the range. This one's a little bit strange because we're collapsing this horizontal line down onto the y-axis. So it's kind of hard to imagine, but imagine squeezing this line, squeezing it perfectly down onto the y-axis, and nothing is allowed to kind of squirt out the sides. It just gets squashed down right onto the x-axis. All we'd be left with is a single point, a single mathematical point, if we squeeze this function down this way and this way. So while the range is infinite, while the domain is infinite, the range is just a single point on the y-axis. And we're only describing range in terms of the y values. We only describe domain in terms of the x values. So what's the one y value in the range? Well, it's just 2. Okay, so we say the range is a single point, 2. And when we want to represent what we call a discrete set, like a single point or a list of points, we use these curly brackets. Right? We don't try to put in interval notation. We use these curly brackets to say, hey, we're listing just a single point or a list of points. So the range on that one is just a single number 2. Okay, this one is a vertical line, so imagine this goes off forever. This vertical line happens to be the line x equals 2, so you can't really see the 2 here, but there's a 2 right there. Okay, and again, we want to know the domain and the range. Okay, well, let's start with the range. The range is squeezing this function down onto the y-axis. because remember the range goes with the y's. So you can see if we were to do that, the entire y-axis would be covered. So the range then is -infinity to infinity. All right, representing the y-axis there. Let's take a look at the domain. Okay, so domain's a little hard to imagine, but imagine squeezing this vertical line down onto the x-axis. And again, nothing can squeeze out the sides or anything. We're just scrunching down onto the x-axis here, squeezing that down, taking this line and just retracting everything down to a single, right onto this x-axis here. The only thing that would be left is the single point at 2. So here the domain is just the single point 2. Okay, so vertical lines have a domain of a single point, and horizontal lines have a range of a single point. But I wouldn't memorize that. Instead, you can just look at it and visually find the domain of the function.